Hi, welcome to Workshop 7 on Data Structures and Algorithms. Today's workshop will focus on the hierarchical data structures. Part of the objectives is to define the terms that are used in hierarchical data structures. We'll also talk about different types of data structures. Our focus will be on the general tree, the binary tree, and the binary search tree. We'll also talk about the basic algorithms to handle binary tree and binary search tree. Under that topic, under that section rather, we'll be looking at how we can create a binary search tree. We'll also talk about how we can insert data and delete data from a binary search tree. Other things we'll be doing will include traversing of binary search tree and how to identify if the binary search tree is balanced. This lecture will be divided into two. This is the first part of the workshop 7, and the second part will be uploaded immediately the recording is done. One thing one may ask is, why do we need to learn another type of data structure after we have learned the linear type of data structure? Yes, in the previous lectures, we've looked at the linear data structure. Well, under it, we have looked at the array, the linked list, and the skip list as types of linear data structure. We have also looked at some of the efficiencies and the worst case scenario and best case scenarios of these types of data structures. Now, linked list, as we have known, linear data structure, as we have known, is good in handling data that are linear in nature, or data that can be arranged in linear form. However, if the structure of a data that we want to work on is not in linear form and cannot be easily put in linear form, then these types of linear data structures that we have studied won't be able to handle those data efficiently. So this is one of the reasons why we need another type of data structure, such that we can be able to manage and handle data structures that are not linear in nature. Another reason why we need to study another type of data structure is because of the efficiency. We understood that, for instance, if we have to search for an item in an unsorted array, and the efficiency will be of the order of n. Reason being that we have to go through all the data items before we can find the item we are looking for, or we end up not finding the item in the array. So that's the reason it is the efficiency is of the order of n. However, other types of data structure might reduce the efficiency or the complexity of the search operation. And if other types can reduce it, then there will be need for us to look at those types of data structures that are capable of reducing the complexity of such operations. So this is another reason why we want to study a different type of data structure from the linear data structure that we have studied previously. Moving into the hierarchical data structure info. The hierarchical data structure is a data structure that consists of a collection of nodes. And that collection of nodes, the nodes in this quote can also be called elements. And each of these elements has a unique predecessor, but it can have many successors. So this hierarchical data structure are also called trees. If you look at this structure we have here, this is an example of a hierarchical data structure. And we can compare it with these three here. We see the similarity of this structure we have with the tree. And that is the reason they are sometimes called trees. Okay, if we can compare the structure we have with these three here, then we can begin to look at part of the tree and compare it with the hierarchical data structure that we have there. In the next slide, we'll be looking at this comparison, and we'll be defining the terms that are used that are used in data structures. Okay, let's continue. The first term we're going to talk about is the tree. A tree is an interconnection of nodes with no closed circuit or loop. This is an example of a tree in hierarchical data structure. If you look at these, we see that these nodes are interconnected. However, they do not have any closed circuit or loop. Closed circuit is, for instance, if this node is connected to this node, then you will realize that we now have a closed circuit of this nature. But in hierarchical data structure, a tree does not have such loop. The next thing is the root node. So a root node, let's compare it with this tree that we have here, the inverted tree. So we all know that this part of the tree is the root. So if this part of the tree is the root, then this part of this data structure, hierarchical data structure, will be known as the root. So for a data structure, the first node of that tree is known as the root node. And the next we're going to talk about is the branch of a tree. The branch of a tree is a link between two nodes within that tree. So this is a node. A link between two nodes is a branch of a tree. So this is a branch of a tree, and this is also a branch of a tree. So this tree, this node A has two branches, which the first one and the second one. And the next, we're going to talk about the subtree. The subtree. So the subtree is a tree rooted at the internal node of another tree. So if we have, for instance, this node, we can say that this is a tree under this node, and this is also a tree under this node. So this node has two subnodes. The first subnode is this one, and the second sub trees. The second sub tree is this one. Then if you want to talk about the node anywhere, then you can say that C is the subnode of A, and B is also the subnode of A. Then let's look at the next term, which is known as the leaf or the terminal node. So if we compare these three with the tree that we have here, we realize that the leaves are the ones at the end of or at the edge of that tree, on top of the tree anyway. So if we compare it with this, we begin to see that that the leaf node is that node that has no successor. If there's any node in a tree that has no successor, that node is a leaf node. For instance, J, K, F, H, and D are all leaf nodes because they don't have any successor. There's no node that comes after them. So these are known as the leaf nodes. And the next one is the degree of a node. The degree of a node. The degree of a node talks about the number of subtrees of that node. The number of subtrees of that node. How many subtrees does that node have? That is talking about the degree of a tree. So if we look at this very well, we see that A has two subnodes. So the degree of A is, of node A is 2. However, B has 3 subnodes. So the degree of node B will be 3. That's how you know the degree of a node. Then let's look at the next one, which is the level of a node. The level of a node is looking at the number of branches on that path from the root to the node, from the root node. So how many paths is coming from that root node, or from that node rather? So let's say it again. The level of a node is looking at the number of branches on the path from the root node to that node. So if, for instance, if you want to know the level of a node C, then how many number of branches do we have from the root node to C? It is just 1. If you not want to know the level of node G, how many branches do we have? We have 1, 2 branches. So it is G is on level 2. Then J, for instance, will be on level 3 because we have 3 branches that lead from the root node to the node we are referring to, which is J. The last that we will talk about is the height or the depth of a tree. So the depth or the height of a tree is the number of nodes on the longest path from the root node to a leaf node. So we first need to find the longest path. And once we get the longest path, then we calculate the number of nodes on that longest path. So there are about 2 or 3 three longest parts in um, this tree. The first part is this part, the second part is this part, and the third part is this part. So each of these three parts that we just mentioned, they have the degree of height 4. The other ones are not up to height 4. Two of them are of degree of height 3. So this is how to identify the height or degree of a tree. And this slide has explained the terms or the terminologies that are used in hierarchical data structures. And we will be looking at these hierarchical data structures and be using the term from the next slide. Another thing I want to point out here is that if you look at this tree, you realize that the number of branches, the number of branches a node can have is not limited to 2 or 1. I mean, the maximum is not limited to 2. So this is a kind of a general tree because it is not limited to 2. When we look at the binary search tree or the binary tree, we will realize that the number of branches a node can have will be limited to maximum of 2. And that one is called the binary tree. But this is the general tree because the number of branches from each of these nodes is not limited to 2. Now moving forward to discuss the binary search tree. We have said a little bit about the binary tree. But in this case, we are now going to talk about the binary search tree. Let's look at the characteristics of a binary search tree. One thing to identify a binary search tree is that every node has a degree of 2 or less. So the maximum number of degree a node can have is 2. A node can also have, which means that a node can have 1 degree or it can have no degree at all. So there's no condition for no degree, sorry. Then if we continue to look at other things that characterize the binary search tree, then we will get to know that the key in the left subtree of must be before the key at the root that's the root node. As the key in the left subtree of the root precedes the key in the root. To put it in another way, it is saying that the node or the value of the item at the left subtree must be less than the value of the item or element at the root node. Another case is that the key in the root node precedes the key in the right subtree, which can also be put that all the elements at the right subtree must be bigger than the element at the root node. And the last says that the left and the right subtrees of the root are also binary search tree. So another thing is that both the right and the left subtrees must also be binary search tree. We will use examples to illustrate these things we've covered here. Remember, the first is that the degree must not be more than 2 from each node. So the degree can be 1 or 2 maximum. Then the second thing is that the node that precedes the node that is at the left subtree must be less than the value of the node at the root, and the value of the node at the right subtree must be greater than the value of the items or item rather at the root node. So if we use this as an example of a binary search tree, then the first condition says that each node must not have more than 2 branches. And if you look at this very well, you see that none of these nodes has more than 2 branches. Then the second condition is that all the sub nodes, all the subtrees at the left-hand side, their values must be less than the value of the root node. If you look at this root node, the subtree is this, or this branch at the left is this. So this 47 is less than 56. And the other condition says that the value of the node at the right-hand side should be greater than the value of the node at the root part. So this is more than this. If you come down to this and assume that this is the root node, then this value should be less than this value, and this value should be greater than this value. If you move down to this, for instance, you also see that this value is less than this value, and this value is greater than this value at the root node. So this is how you will know if a tree given to you is a binary search tree or not. Let's look at this activity, which is to determine the maximum number of nodes in a binary search tree of height n. So n could be any number. In this case, we have been given that we are looking for the maximum number of a node of height 1. So what do you think will be the maximum number of nodes that has height 1? Remember what height is looking at, or the definition of height or the depth of a tree. It is the number of nodes on the longest path from the root node to the leaf node. So if we have the number of nodes or the height to be 1, so the number of nodes from that root path, from the root to the leaf node will be 1, because we'll have only a root node like this. However, if the maximum number of the binary search tree, to calculate the maximum number of nodes in a binary search tree of height 2, then what do you think we will have? The height 2 is when we can move from the root node to another node before it, which is going to tell us that we can have one node here, and because we are looking for the maximum that we can get is when this node has 2 branches. Hence, the number of nodes, the maximum number of nodes will be 1, 2, 3. If we continue that way, to look for the maximum number of nodes in a binary search tree of height 3, So if we have this to be height 2, so the height 3 will be when we have another node after this node. And we are looking for the maximum number. So we fill this node, ensure that the node is completely filled. Then we have another node here, and we have another node here. So looking at this, if we calculate the number of, count the number of nodes we have at this level 3, the height 3, then we'll get 7 as the number of nodes. Do you understand how we have gone through this? If that is clear, then we will continue. And another thing that we may have to look at is do you see any kind of sequence in generating this maximum number of nodes? Can you find any sequence to represent this? Yes, we can use this sequence, this formula, for instance, to represent how we can calculate the maximum number of nodes in a binary search tree of certain height. So for instance, if we have the height to be 2, then we replace this n with 2, and we get 4 minus 1, which is 3. Going further to look at this one, if we have n to be 3, then we replace n with 3, and we have 8 here, and 8 minus 1 will give us 7. So this is how we can calculate the maximum number of nodes in a binary search tree of a given height. So let me clear this drawing. Then there's a question which says, what about the minimum number of nodes for a binary search of a given height, binary search tree of a given height? If we follow the pattern we use, we can get to know the minimum number of nodes in each height of, sorry, the minimum number of nodes of a binary search tree of any given height. We can also generate a formula to represent or to generate how these can be calculated. Let's now look at an algorithm to search for an item in a binary search tree. Assuming we have the same tree we had previously in the previous slide, how are you going to find a particular item or element in that tree? Remember, we said that a binary tree, that all the sub-elements at the left-hand side are all the sub-elements at the left-hand side must be smaller in terms of value or come before the root node element. And all the elements at the right-hand side must be greater in terms of value or come after the root element. So if we have that understanding, we can use it to drive and write down the algorithm for searching an item in a binary search tree. So if you go through it, we say that we first of all check if there is a tree. And if there is a tree, the first place we have to move to is to look at the head or the root node. So if the item that we are looking for is at the root node, then the operation will terminate at that point. However, if it is not at the root node, the operation continues. And how will it continue? It will compare the value of the root node with the item or the value that we are looking for. Then if that value is less than the root node, then we will move our search to the left part, to the left subtree, and perform the same operation by looking at the root node and checking if the item at the root node of that left subtree is equal to the item we are looking for. Otherwise, we continue the process of either moving right or moving left. Then if that is not the case, that is when the item that we are looking for is greater in terms of value than the item at the root node. Then we have to move to the right subtree and keep searching through the right subtree to find our element or the item that we are searching to find. So in each of these terms or in each of these operations, either moving to the left or moving to the right, we will look, if you look at it very well, we will realize that we have recursive call. That's a repetition of searching, comparing if it is going, is it greater than the element at the root node? No. If it is not, then it moves left. Then if it is, then it moves right. It goes to that level. That particular element where it has moved to will become the root node, and it will do the same comparison. So it keeps repeating recursively what has been done before. So this is the approach that one will use to find an item in a binary search tree. Now, what do you think will be the efficiency or the best and worst case scenario? Remember that if the item that we are looking for is at the root node, then the search operation will end at that point. So the best case scenario is when the item is just located at the root node. But if the item happens to be less than or greater than the item at the root node, then we either move left or move right, respectively. So now, when we move left or move right, we recursively do the same thing until we get to the leave node. So in looking at this again, we realize that we are not going through all the data items in that tree. We have a way of reducing them in half as we proceed towards the leaf. So that will give you an idea of what the efficiency of a search operation is in a binary search tree. Now, let's use this as an example to illustrate what we have just studied in the previous slide. So we are still talking about how we can search for an item in a binary search tree. And the example we are using is that we want to look for item 5 and item 61. So how do we go about this? First, we have to check if the tree exists. Yes, of course, the tree exists. We have a tree here given to us. Then we have to look for 5. We compare 5 with this root node and realizing that 5 is less than the root node. It's not located at the root node, and it is less than the root node, then we have to move towards the left subtree. We perform the operation again by comparing these 47 and 5. Is it equal to 5? No. then is it more than or less than 5? It is more than 5, so we'll move to the left. And we'll compare the same 5 with this root node, realizing that 5 is not equivalent to this, and 5 is less than this, we move left. We do the same thing here, and because it is not equal to 5, we need to leave this node. But if we are leaving this node, there is no other node after this node that we can search to find to see if we can find the item 5 that we are looking for. So this will end our search at this because we can go further from this place. But if we are looking for 61, then we move from the root node again and check if the root node has the value 61. No, if we look at it critically, we understand that the root node is not having the value 61. So we compare the value to see if it is greater or less than 61. But because 61 is greater than this, the rule for binary search tree or search operation is that we have to move right because it is greater than the item we have at the root node. So if we move right, we get to this place, we check if this is equal to 61. It is not. Then we check is 61 less than this? Yes. Then we move to the left. We perform the operation here because this is not equal to 61 and 61 is greater than this item, then we have to move right. So this is what we do again at this point. On realizing that that node does not contain the item we are interested, we have to leave that node. But where do we move to? Are we going to move to the left subtree or move to the right subtree? Because 61 is less than 62, then we have to move to the left subtree. So if we get to this point, we will see that we have gotten to the position where 61 is. So we end our search at that point. Now, this is a list of the path that we need to take. For instance, when we want to get to 5, we have to check this, then go through 47, then go through 22 until we go to 11 without finding 5. And if you want to look for 61, we have to go through 56, again, go through 69, go through 59, go through 62, then we end up finding 61 at this point. So these are the steps that one needs to take for one to be able to search for an item in a binary search tree. Okay, let's continue. Moving to the next slide, we have activity 2.7.2 rather, and it wants us to find the path that it can follow to search for nodes 61 and 28. Going through that, we have already looked at how we can find the path for node 61, and we can go through it again and also go through how we can find the path for node 28. So for node 61, to find the path, we have to go through the root node. See if the root node is equal to 61, because if it is not, then we have to check whether it is before or after 56. So the node 61 is after 56, so we have to move to the right subtree. Then compare it with base 69. it is not equal to 61, and the node is less than 69, then we move to the left, subtree. And at this point, we compare it with this value because it is not 61 and 61 is after 59, we move to the right. And we do the same comparison here, then realizing that it is not equal to 61 and 61 comes before 62, we move to the left. And this is the position where we can find the node 61. And if we take the same step, we'll look for 28. We have to go through this part, move to node 47, and move to node 22. Then 28 is after 22. Then we'll move to node 29, and 28 is before node 29, and we move to node 23. And at 23, we can't move to anywhere else. We'll come to the stopping point, and we conclude that node 28 is not in the structure or in the tree. That's the step, how we can get it for the node 61 and for the node 28. So what is the height of this binary search tree? What is the height of this binary search tree? I'll leave that question for you to answer. Remember, you need to look from the root node down to the leaf node to know the height of the binary search tree. What is the level? What level is 22? So what level is this node 22 on? You know, the first node is on level 0. The second node is on level 1. So level 22 should be on level 2. Then we have, what is the maximum possible height of another binary search tree containing these nodes? Draw the binary search tree. So if you have these nodes, what is the maximum you can get? You can get the maximum by looking at another way of rearranging all these nodes to maintain the same rule for binary search tree and end up getting the maximum height or a height that is more than this height. Can you draw it? You can draw it by looking at a position like this, where you have the highest item in the list, and you begin to arrange every other item that is less than that item at the previous node, that way until you get to the end. So this will give you the maximum height of the nodes that we have in the previous tree. So how do you find the minimum? You can find the minimum if you rearrange them to look like this, and you see that the minimum height will be achieved at this point. Because at this point, every node in this tree has a maximum of 2 branches, and that conforms with the rule for binary search tree. If we go further to check if the answer to question 4 is also in accordance with the rule for binary search tree. So if you look at this place, the binary search tree rule says that a node must not have more than 2 branches, but you can have 1 branch. So you see, each of these nodes has only a branch. So it conforms with the rule for binary search tree. Moving back to question 5. So this is the minimum that you can get, and that way the final answer, the last answer, sorry, the answer to question 5. Now let's move to building or creating a binary search tree. We want to create a binary search tree using these data items that we have on the left. We have 10 data items given to us, and we want to use them to create or build a binary search tree. How do we go about doing this? We have to first of all look at the first element. When we pick the first element, we will check if there is a tree existing. If there is no tree in existence, then that first element will become the root node. So we have to position the first element as the root node. Then we move to the second element. When we get the second element, knowing fully well that we now have an element at the root, then that first element will not become the root element. Rather, we will check where we have to position it, either at the left or at the right-hand side of that root node. Then, well, for us to do that, then we have to consider the condition for placing them either at the right or at the left. And the condition says that if the element is before the root node, then it should be at the left. However, if the element is after the root node, then it should be at the right. For this case, the element we are considering is we are looking at them in alphabetical order, and we want to consider the first alphabet in each of these words. So, for instance, J is after I, so it should be at the right. Then we take the third one, do the same thing, and place it in the tree, and take the fourth one. We'll continue that process until we get to the final element in the list. So at the end, what we are going to have is this, because the first element there is this iron, and it will be here. The second is joy. Joy is after iron, so it should be at this position. Then the third is an is before iron, so it should be at the left position of an iron. Then the fourth is dot. So dot is at the left position of iron and is at the right position of an. So we keep going that way until we get to Kim. So for instance, Kim being the last here, Kim is after iron and it is after joy. However, it comes before Sam, and it also comes before Roy. So it should be positioned here. Now, let's look at the algorithm for building a binary search tree. So the algorithm for building a binary search tree is we first check if the tree is empty. And if the tree is empty, that first node will become the root node of that tree. But if the root node is not, if the tree is not empty, that implies that the root node is occupied. Then we will compare the element that we want to build with the root node. And if it happens to come before the root node, then we move to the left and keep going until we find a place where we can place it. Otherwise, we move to the right and keep repeating the same process until we find a place where we can place that element. So if we have, for instance, this example that wants us to insert an item 60 and 28 into this data, into this tree. How do we go about it? Let's start with 160. So 60, we already have a tree, so it is not an empty tree. And looking at the node tree, sorry, the root node, we realize that we cannot insert 60 here. We cannot insert 60 here. Let me put it this way. For you to insert, if you look at what we did in the previous one critically, you will realize that for the insertion to take place, it must be at the leaf node. It must be at a place where there's a space. So for instance, you can insert a data here as long as it corresponds and goes with the rule, or you cannot insert any data at this point. That is for the binary search tree. Now let's continue. So we've checked and 60 is more than 56. So we need to move right. Then we check again, 60 is less than 69. Then we move left. Then 60 is greater or comes after 59. Then we move right. Then 60 comes before 62. And we move left. So this is the root node, sorry, the leaf node. And it is at this point that is expected how we should insert the element into the tree. But the question is, where do we go to move to? Do we move to the right or move to the left? So because 60 is less than 61, then we have to move to the left. So we insert 61 at this point. Now, if we follow the same process, we will go through the same, follow the same process we used in inserting 60. We'll end up inserting 28 at this position. So these are the steps that we can take to insert an element or an item into a tree. Okay, so we are now going to move into the balanced binary search tree. How do you know a balanced binary search tree? A balanced binary search tree is a tree where all the paths from the root to the node of that leaf, sorry, to the leaf node of that tree are of the same length. So if you have any tree where all the paths from the root node to every leaf node within that tree is the same, then you know that that tree is balanced. So if we move backward a bit, do you think this tree is balanced? Do you think it is balanced? It is not balanced because if you look at the paths, for all the paths to the leaf node, the height or the length of all the paths to the leaf node is not the same. So this is not a balanced binary search tree. But this is an example of a balanced binary search tree. So a binary search tree, in other words, a binary search tree can be balanced or unbalanced. So if you have if you have a binary search tree similar to the one we saw in the previous slide, you notice that that one is not completely, but it's not a balanced. It's not a balanced binary search tree. So now let's look at this activity 7.4. Activity 7.4 has the first question as, what is the smallest height of a binary search tree with 42 nodes? What is the smallest height of this search tree, binary search tree. These questions will be a kind of an exercise to you. I expect that from what we've done, starting from the previous slides, you've come to understand these questions that are asked here. These, these are also similar to those questions we answered in the previous slides. So I will leave these questions for you to go through. And if you have any concern, then you can let us know during the tutorial section. But if I am to give you a clue, I'll say that you can draw this table. If you want, you can just draw the table, the tree, by looking at the tree in this way, that you have the first height, then you look for the first height, and you continue to draw it like this until you get 42 nodes. So if you have the 42 nodes, you now look at what is the smallest height of that binary search tree or binary tree with 42 nodes. That is one approach to find out the height of the smallest height of a binary tree with 42 nodes. So if you can answer the first one, then you should be able to answer the second one, because the second one is talking about the maximum number of nodes for a binary node in a binary tree of height 5. So if you know, remember that the height of a node is the number of nodes on the longest path from the root node to a leaf node. So if you have like a node that is has height 5, you should be able to know the maximum number of nodes in that binary tree. Another question is, what happens if you use our algorithm to create a binary search tree from a sorted list? This question was answered in the previous slide. If you use it to create an algorithm, if you use our algorithm to create a binary search tree from a sorted list, then you have a list that goes either this way, if you arrange them in ascending order. In descending order, you have a list that goes from the top to the left. Or if you arrange them in descending order, you may have a list that goes from top to the right. For instance, the list that you're going to have will look like this: 1, 2, 3, 4, 5, and it continues. And if you look at it again, it will increase the height of that particular tree that we've drawn. So that's why it is always necessary for one to look at the list very critically and understand how the list can be arranged. To describe the shape of the tree we want and explain why we want a tree of this type. So if you look at the tree that we just saw, we can see that the tree keeps going. And if we are to search through this tree, then we can search them level by level. However, if we have a balanced tree is a tree that is all the, just like the one we saw in the previous 2 or 3 slides, you will realize that the level of that tree will reduce in number. And that is the kind of shape that we want in this binary search tree. So we want the smallest height, that's it. We want a tree that gives us the smallest height. When we have the smallest height, then it will increase the efficiency of searching an item within that tree. So this is where we're going to end this part one of workshop 7. A quick recap of what we have done. We have so far looked at the binary search tree. We have also discussed why we need to study the hierarchical data structure. We've looked at examples of this hierarchical data structure. We looked at the general, the binary, and the binary search trees. We also inserted, and also we have inserted an item into a binary search tree, and we've demonstrated how we can create a binary search tree. So we encourage you to go through this again. If there are sections you think you need some support on, then please let us know and we can support you on that. Also go through the exercises and attempt the quiz for the workshop 7. And remember, there will be another part or part 2 of this workshop. Thank you so much and see you next time.